Today we will start mobility. Mobility of charge carriers. Conductivity arises from mobile charge carriers. Arises from mobile charge carriers. For metals, mobile charge carriers are electrons. For gases, mobile charge carriers are electron and positive ion. Mobile charge carriers are electrons and positive ion. For electrolytes, mobile charge carriers are positive and negative ions. Mobility is defined as mu is equals to drift velocity upon electric field. Drift velocity by electric field is defined as mobility. Unit of mobility is meter square volt second. Meter square volt second. Mobility is always positive. As we all know that drift speed is defined as charge of electron into electric field upon mass of electron and relaxation time into relaxation time. So mobility is also defined as charge of electron upon mass of electron into mobility into relaxation time. This is one also. So from this we can say that mobility is directly proportional to the relaxation time. Means greater the relaxation time, greater is the mobility. And mobility is inversely proportional to and mobility is directly proportional to. Now limitations of Ohm's law. Although Ohm's law has been found valid over a large class of material, there do exist materials and devices used to electric circuits where the proportionality of V and I does not hold. As we all know that Ohm's law has been found valid over a large of materials. There do exist materials and devices used in electric circuit. There do exist materials and devices used in electric circuits where the proportionality of V and I does not hold good. First, V ceases to be proportional to I. It means the graph between V and I should be linear like this. But in the case of good conductor, the graph comes like this. It will deflect from a linear property, means V does not stand for V does not directly proportional to I. Second is that point B. The relation between B and I depends on the sign of B. In other words, if I is the current for a certain V, then reversing the direction of V, keeping the magnitude fixed, does not produce a current of the same magnitude as I in the opposite direction as I in the opposite direction. This happens, for an example, if we take a diode, this will happen. Okay, example diode. If we see the characteristics of diode, we see that it was not linear, but in reversing direction it will not be same. Now we see the third point. The relation between B and I is not unique. That is, there is more than one value of B for the same current I. That means there is more than one value of V for the same current I. A material exhibiting for the same current I. A material exhibiting such behavior creating such behavior is GAS, gallium arsenate. So we can now see the variation in current versus voltage of GAS, which is gallium arsenate. This is voltage axis, this is current axis. It will give like graph in which this portion and this portion are divided. This is non-linear region. This is negative resistance region. Now we see the resistivity of various materials. First of all, we define what is resistivity. Now we see the temperature dependence of resistivity. How temperature will depend on resistivity, we will see in this. Okay, the resistivity of material is found to be dependent on the temperature. Different materials do not exhibit the same dependence on temperature. The resistivity of a material is found to be dependent on the temperature. there is this relation between resistivity and temperature dependent, that resistivity of temperature and resistivity at 0 degree centigrade 1 plus alpha T minus T naught. This is the relation where rho T is the resistivity of the temperature T, rho naught is resistivity at reference temperature. Alpha is called the temperature coefficient of resistivity. Coefficient of resistivity. The dimension of alpha is inverse of temperature. The dimension of alpha is temperature inverse. For metal, alpha is positive. For metals, alpha is positive. For metals, alpha is positive.